In this video, we'll look at how we can fit a quadratic relationship between y and x. So here's an example from a paper on how innovation varies with the level of competitiveness of an industry. So the authors here are using data on different manufacturing firms in different industries. And the different industries, so think really detailed industries. Some of them are making tools, some are making tires, some are making children's toys, appliances, things like that, okay? The industries are being measured according to how competitive they are. So 100 is perfectly competitive, like the textbook model from intro econ, right? And then lower levels are less competitive. And the measure of innovation here is patents per firm. So a measure of how much innovative activity goes on, how much the businesses are patenting new ideas or technologies. Not all patents are sort of created equal, right? Some are more important or more innovative than others, and those tend to be higher cited. So they're using the citation-weighted patents per firm. Okay, and you can see that there is a sort of quadratic, like an inverted U relationship between y and x here. Okay, and in the paper, the authors propose that this might be the result of two competing effects. So with more competition, you can get certain incentives for higher levels of innovation or lower levels of innovation, right? And one of the mechanisms here is more competition. You think about that zero economic profit condition under a perfectly competitive market structure, right? And there could be lower incentive then to innovate because all firms are like homogenous. They really can't distinguish themselves from one another in the market. All right. But at lower levels of competition, the authors think that, as the level of competition gets higher, firms might still be able to differentiate themselves, right? And so there might be a higher incentive to innovate to escape competition. And so both of these mechanisms, they think, might be operating behind the scenes in such a way, depending on sort of the relative strengths of the mechanisms, as to produce that inverted U shape. In our regression, we can capture this by including both x and x squared as explanatory variables. Remember that linear regression is linear in the parameters, so the 3 betas here. That's still true. It doesn't necessarily have to be linear in the variables, all right? So this is a perfectly valid thing to do. The sign on beta 2 controls the overall shape of the regression fit, okay? So if we have a situation where beta 2 is positive, that goes with this U shape, this convex parabola. And on the other hand, if the relationship, like we saw in the previous slide, has this concave inverted U shape, then that's going to be described by beta 2 being negative. Right? Just think that as the value of x gets large enough, the sign on the x squared term is going to determine which way the slope is. Okay, so if that coefficient's negative, it'll eventually turn down. If that coefficient's positive, that relationship will eventually become positively sloped. We couldn't do this with the log transformations that we've already studied because log of a variable is a monotonic transformation. Okay, so to fit this non-monotonic relationship up, downward sloping then upward sloping, or upward sloping then downward sloping, we need something like a quadratic function here. Okay, a characteristic of this quadratic relationship is that the rate of change between y and x, or like the slope of this line right here, the best fit line, itself changes as x changes. And to see how that works, what we can do is write out the estimated regression equation. Like so. And then differentiate this with respect to x. So this is a constant. Derivative will just be 0 with respect to x. Derivative of this, just beta 1 hat. Now notice in the special case where we don't include the x squared term, or its coefficient is 0, this is the standard case where the slope between y and x is just constant. It's whatever that beta 1 hat is. Here, though, we have another term, so we apply power rule to this. We get 2 times the constant in front, the coefficient, beta 2 hat, times x. like so. All right, so one thing I want you to notice is that rate of change or slope itself is varying as x varies, and that matches the graph here, right? We have upward sloping, less upward sloping, got a spot where it's 0, downward sloping eventually, right? So that that slope or rate of change of the line tangent to that curve is varying with x. And again, we'll call this derivative object either the slope, or I might call it rate of change. Okay, so x and x squared could be used in a situation like this to capture a u-shape or inverted u-shape between y and x.